Hello everyone. Today I'm going to take you through a little tutorial that explores primitive geometries in Rhino in 3 dimensions. So I know that up to this point your Rhino experience has been all about what goes on in the 2-dimensional realm. You guys have been playing with plans and sections and correlating them, diagramming, hatching, whatever. And I also saw that you guys were playing around with unrolling some of these 3D shapes in the 2-dimensional. But we're going to take some steps into understanding how Rhino works when it's dealing with 3-dimensional shapes. So here I have probably the most basic building blocks of Rhino geometry, and that is the cube, the cone, the tetrahedron, and the cylinder. So I assume that most of you are familiar with these. Maybe not the tetrahedron. At least when I was in your position, I was not either, so I thought I might explain this one a little bit more. It is a 4-sided shape where each of the sides is an equilateral triangle, and it is circumscribed within a cube. So you can see sort of maybe how that works, but we'll get into constructing it, and I think we can understand it a bit better then. So just to start, I want to admit to you that there's hundreds of ways of constructing each of these shapes. There are easy ways, there are hard ways, there are ways in between. And I don't know all of them, and I will only cover, a couple of the ways. But if you find other commands that do the same thing and it works better for you and it's faster, just do that, it's fine. I'll just show you some routes that work for me, and it's also not that complicated of a thing either. So the first way is probably the most generic, and it's to type out, it's command-based. So you type out the command. If we're dealing with the cube, we'll type the command box. And by the way, you don't have to click in the command bar every time you type a command. You can just start typing away, press enter, and it will automatically queue up that command. So when you type in box, it asks for the first corner of base, and now you can see I'm sort of zooming around here. Now if you hold shift, it'll create a square base profile, but you can also just type in the dimension. So we'll use a 5-foot length, or a 5-foot width, and then a 5-foot length, and then it asks for the Z parameter, and we'll use a 5-foot height as well, because that is the definition of a cube. Change that to our little solids layer so that it matches, and there is a cube. A cone works the same way. Type in the command cone. You will press for the center base point and then your radius. And since we're working with 5-foot intervals, we'll type in 2.5-foot radius. And then it is going to ask for your Z height. So you can either snap to another existing point, you can go negative, positive, whatever, or you can type in what that vertical constraint is. And that will give you a 3-dimensional cone. Tetrahedron doesn't have a command, but we'll get into constructing it when we construct all these others. And then there is cylinder. So cylinder, again, press, which is the center point of your base, just like the cone, and then we'll define the radius with 2.5 feet, also just like the cone, and then you define your Z height. So we'll use 5 feet as well. And then we have a matching set of these little cube, cone, and cylinder. The next way of constructing things in Rhino, and this is my preferred route over using the commands, is constructing it using curves. So we'll switch to our curves layer, and then we will, for the cube, we will type in rectangle, the command, and then define what we want to be our base. So this time maybe we'll go crazy with it and make a 10-foot base. Cube, 10 foot by 10 foot. 10 foot, enter, and then 10 foot, enter. Now we have this base profile, and now we'll use the command extrude curve. This is a super useful command, and you'll see that it's, I guess, lifting up this curve. You can think of it like that. And there's all sorts of options. You can do the both sides option where it, lifts up and lifts down the curve about the center. You can do solid yes or solid no, and that makes it so if we do not want both sides. If we don't want it to be solid, and we'll just do that, you'll see that we have a open extrusion. So in Rhino, closed extrusions or closed solid poly surfaces are like the gold standard. That's what we always want to have. And there's all sorts of benefits to having closed solid poly surfaces as you progress through architecture. And it also just forces you to make clean, good Rhino decisions. And in order to get this open extrusion to a closed solid poly surface, we will either type in the command surf point, and that will ask us to specify a surface using 4 separate points, snapping to each corner, and that gives us our cap. And we can copy that to the bottom, or just to try another route, we can click on that base curve that we specified and type in planar surface, press enter, and now we have both a bottom and a top cap. So selecting all of those, because they're still unjoined even though they appear to be closed, selecting all of those, we can join it, and now when you have it clicked over in object properties, it says it's a closed solid poly surface. So moving on to the cone, I guess we'll switch this layer here. Moving on to the cone, we'll do a similar step as we did for the cube. We'll define the base, and we can do that with the command circle. Click the center of circle and then define the radius. Let's go with, a 5-foot radius. And now we want to define our z height. So to do this, we'll type in line, and then here you can see the option vertical, and this allows you to draw a line in the z-axis. So type in V, press enter, and now wherever you draw this line, it will be constrained to your vertical direction. It's a super helpful little tip to know. And with the center snap on, we'll hover our mouse sort of near the edge of this circle, and it'll pop up that little Sen logo or whatever label. Click, and now our base point for that line is at the center point of the circle. So lifting up, we can just let's make a huge cone, really tall, like I don't know, Christmas tree or something from whatever. And then we will connect the top point of this cone to any point along this edge. I sort of like to have it there, just at the midpoint of that circle, or the starting point, just so that it fits in the orthographic, or it's a little bit cleaner. And you can see that we now have sort of the linear wireframe for a cone, but it's not a solid yet. So to make it a solid, we'll type in the command rail revolve, where we will take this curve that's sort of the outside line, and we will send it around, we'll revolve it around this base point. And so let's just do it. Select the profile curve there, and now it asks us to select the rail curve. So we do that, and then it asks for the rail revolve axis. So the axis that we want to revolve it about is this vertical z-axis. So select the base point, and then any point along here, I'll select the top, and we have ourselves a cone. You'll notice that using this command, we don't end up with an automatically closed solid polysurface. It is just a surface. And this time, rather than doing the planar surface or surf point, we will just type in the command cap. And sometimes, if you have a simple enough open polysurface with a single or, in some cases, two openings, Rhino will be able to interpret that into a closed solid polysurface. So typing cap will cap it, make it solid. Now for the tetrahedron, I'm actually gonna change this layer. We've gotten a touch large. Maybe move us over here, our workspace. So now to construct the tetrahedron, we will take this big cube that we've constructed and we will copy it over using the Boolean, or using the gumball and the Alt key to copy it. We'll take it over here and type in the command extract wireframe. When we extract the wireframe, it'll take all of these sort of just geometry defining, like edges and subdivisions, and it will turn them into curves, the curves that we know and love. To make this a little bit clearer, we'll get rid of these subdivision curves. Highlight them, delete, so that we're just left with the edge curves. So now that we're here, you'll notice if we hide that tetrahedron, this is our wireframe for it. So to make that wireframe over here, we'll connect diagonal points and then connect the opposite diagonal points on the top and bottom. And it can be either way. And now we'll just connect from here to here, from here to here, from there to there, and there to there. So you can see that we have now developed that wireframe for it. And using the planar surface command, we can now generate each of these surfaces and then selecting each of these surfaces, we can type in join and make it into a closed solid polysurface. So finally we'll do the cylinder. And to do this, we will use the circle command, click to define the center, and then type in the distance, or you can click on your screen that defines the radius. And then just like we did for the cube, we will type in extrude curve with that curve selected. This time we're going to keep solid on, that way we don't have to do anything at the end, and just extrude to solid. And let's extrude it 10 feet tall. Use this as a reference point. And that is how to extrude a solid cylinder. So now that we've gone over how to model all of these primitive geometries, we're going to talk about surface isocurves and curves and how those relate to one another and relate to the geometries themselves. So you'll notice that this little first group, they are just the geometries. All you're seeing is the tetrahedron and the surfaces of it. Same for the cube, the cone, and the cylinder. But generally, when you're modeling, the geometries that you model will have these little sort of light lavender lines, or they'll be whatever color you have selected for your layer. These lines are imaginary lines that don't necessarily lend you any ability to further modify the geometry itself, but they're a way of visualizing the way that Rhino thinks about the geometry. So it's how it's subdivided, it's how it's calculated, and you can see that. While these lines can't be modified directly, when you click on the surface or the shape, you can't necessarily click on these lines. You can extract those lines into curves that you can then modify, and those will lend you great ability to make beautiful drawings, etc. So now that we've gone over some basic principles of surface isocurves as they relate to our familiar primitive geometries, let's talk about them specifically, how to modify them and how to work with them. So first, I guess you'll notice that none of these geometries have any isocurves on them. So to fix that, we'll select them all, and then over in Object Properties up here, and go down to Isocurve Density. We can click this checkbox, Show Surface Isocurves, on, and now you'll notice that we have those lovely little thin isocurve lines. But let's just say this cube, when you turn those on, is divided into 4 parts, but we really want it to be divided up into 12. In order to modify those, we'll do that using the rebuild command. Now, the rebuild command doesn't work on closed solid polysurfaces. So before we do anything, we'll need to select them all and do the opposite of joining the surfaces, and we'll explode them. So once you explode them, you can click and select each individual surface without selecting the rest of the shape. And now that we've done that, we'll select the surface that we want to rebuild, and we will type in the command rebuild. And this will provide us with this lovely little pop-up. This pop-up allows us to select the amount of subdivisions we want, and you'll see as I'm clicking through that, it's previewing for me what that looks like, what those subdivisions look like for me. So if we want 12 subdivisions, we'll change the point count to 12 in the U direction and 12 in the V direction. The number in the parentheses has to do with the original number of subdivisions before you rebuilt it. And U and V are the way that digital modeling softwares, it's the coordinate system that they use. So every surface is divided up in the U and V direction. They can sort of be thought of as X and Y, although they do also apply to curved and double curved and flat surfaces as well. The degree has to do with the 1 refers to a planar surface and 3 refers to a curved surface for our purposes. You can delete the initial surface, which we're going to want to do. We'll replace it. And you also are going to want to keep the retrim button on. It doesn't have any applications now with the cube, but I'll explain it later relative to the tetrahedron. So now, with 12 divisions in U and 12 divisions in V, we'll click OK, and you'll see that our surface is perfectly divided how we would like it to be. This can be repeated with all the other surfaces to end up with with the 12 divisions in every direction for the cube. Now moving on to the tetrahedron, just to demonstrate what the retrim button does, we'll type in rebuild, selecting one of the surfaces, and you'll notice that there's this sort of ghost area, this ghost surface off here. So if we don't click retrim, it will build this surface, because the triangular surface is thought of in Rhino as just 1/2 of a quadrilateral surface. So we'll click retrim, divide it in 12 divisions, select OK, and now we've changed the division number. Now we'll rebuild the final surface, the cylinder. So select the surface and type rebuild. And again, it'll pop up the window we're familiar with. And you'll notice that for the cylinder, it divides it how it would, but these divisions in the V direction, they don't really help us that much. They actually obscure the geometry more than illuminate it for us. So let's cut those down to 2. And now, with the 12 divisions in the U direction, I think it helps us understand the geometry of the cylinder a little bit better. It's also really important now that we understand the degree function. So with a cylinder, because it's a curved surface, if we take it down to the degree of 1, it will turn this into straight sections, meaning that we'll end up with a faceted cylinder at the end. And since that's not what we want, we can move it up to 2, which is what it was before, and then we'll rebuild another curved surface. So click OK, and we end up with this nicely divided surface. Moving on to the top, when we attempt to rebuild it, we run into a bit of a problem, because Rhino thinks that this is a it hosts it as a quadrilateral surface that's been trimmed to the shape of a circle, which means that the top, if we rebuild it in the U and V direction, let's just do it, it doesn't coordinate with the U and V direction that we've rebuilt for the side of the cylinder. So to get around this, we'll just have to construct those lines. To do this, I think we can first we'll want to move to the curves layer we have, and we will, with the center snap on, select a center point, and then select a side point that perfectly snaps to one of these locations. We can do that by, if we know the radius of our cylinder, we can hold shift to make sure that it's in the orthographic, and then type in 5 feet, hold shift, and press enter, and then click. And now our curve is perfectly in that direction. Now what we'll want to do is we want to array it around this circle. And a standard array is going to array a curve or an object in the Cartesian polar system, or the Cartesian grid system. But we want to array it in the polar coordinate plane. So we'll type in array polar, and that will allow us to array it in a circle. It asks for the center point, so we'll click there. Number of items, we have 12 because that's the number of subdivisions we have. Press enter on that, and then it wants to know the angle to fill. We want to array it all the way around this circle, so that's 360 degrees, which it already has in there, but if it doesn't, type it out, press enter, and now the preview shows it arraying this curve, and each piece matches up perfectly with our U divisions. Press enter, and we're left with that. To complete this, we can select the curves that we just arrayed, copy and paste them, and then move them up whatever height we have, which is a height of 10 feet. Finally, we can extract the wireframe for this shape, and we end up with this wireframe. I think it's helpful to delete this center line that you end up with, because it just obscures the geometry of the cylinder a bit. You can repeat these steps, extracting the wireframe and rebuilding every surface so that it has even divisions for every shape or every geometry to end up with perfect wire. When you finish rebuilding all the surfaces with your desired amount of divisions and extracting the wireframes, your wireframe should end up looking something like this.